Hello and welcome back to another fun and exciting lesson in Algebra 2. This is Mr. Bean. Today we're going to talk about solving equations, in particular exponential and logarithmic equations. So to do this, we'll first start off with using what's called the properties of equality. And what we do with that is if you have bases that are the same, notice here we have a b base and a b base. If those are the same, then we can just take the exponents, x and y, set them equal to each other and solve. Real simple. Same with logarithms. If you have bases that are the same, you can basically just say, hey, those bases are gone, and it's just x and y, and then you can solve it. These little conditions here state that the base has to be greater than 0 and it cannot equal 1, okay, or else this wouldn't work. But if you are greater than 1 or greater than 0 and it's not equal to 1, you can use this. So here's how we do it. First thing is try to get these bases to be exactly the same thing. And I could change this 49 and make it 7 squared, because 7 squared is 49, and then there we have a 7 on this side. Now we've got bases that are the same. We've still got to write this whole thing out here. So we have 3x plus 4 in the exponent. That's a plus right there, plus 4. And then we have our equal sign. So 7 squared is being raised to the 2x plus 1. And now at this point, since the bases are identical, you can take the exponents, which is 3x plus 4, and set them equal to each other. Here, a power to a power means you multiply. And so be careful here, because that means you are distributing to the entire exponent. So we now have 4x plus 2. And now combine like terms. So how about we subtract 3x to both sides? That gives us an x over here on the right. Subtract 2 from both sides, and you get 2. So x equals 2. Look at that. Beautiful. Simple. No problem. See how easy this is going to be? Equating exponents. Number 2. Let's try this one. So now we have, get rid of that. So now we are looking at how can we make these bases be exactly the same. This 25, I could turn that into 5 squared. And then I would have raised to the 2x plus 3. And then my equal sign. Now, what can I do to the 1/5? How can I make this become base 5? It is the same thing as 5 to the negative 1. That's what 1/5 is. Remember this cool negative exponent trick? Makes it the reciprocal. And then you have that being raised to the 7x minus 1. And now, since we have bases that are the same, 5s, we equate the exponents. Just remember to be careful that we are power to a power means you multiply. So we take this negative 1 and multiply it and distribute it through to the entire exponent. So now on the left side, we have 4x plus 6. And here's our equal sign. On the right side, we'll have a negative 7x plus, this time 1, plus 1. And how about I add 7x to both sides? That'll give me over here an 11x. And then I'll subtract 6 from both sides. That'll give me negative 5. And then x equals negative 5/11. And there we go. All right, you're going to try number 3. So play around with this number 3 here. See if you can get these bases. We're going to change 64 and 1/16 to make it become the same base. Go ahead and pause the video now. Okay, before I show you the rest of this, I wanted to at least get you started, and that is 4 to the negative 2. 1 over 16 can become 4 to the negative 2. 64 can be 4 to the third. So see if that helps you out a little bit and keep going with the rest of this problem, if you don't have it already. And you should have come up with m equals 5 over 6, 5/6. You can see here my steps. I just had to distribute the negative 2, and then I would have my 6m minus 2, and again, equate the exponents. So again, solving by equating exponents is if you can create the bases to be the same, then you can equate the exponents. All right, now we get into the fun stuff with solving exponential equations and taking what's called a logarithm of each side. Now, if you remember, at the beginning of logarithms, I taught you that division and multiplication were inverses of each other, just like addition and subtraction. And so when we are trying to get rid of division, we multiply. Or if you're trying to get rid of addition, you subtract. That's how we cancel things out. We use their inverses. That's going to be the same thing with exponents and logarithms. So if we see we have a variable up here, we're trying to pull this out, then we're going to use a logarithm. So what we're going to do is take the logarithm base 4 of 4 raised to the x. Okay, so what I do is I take the log base 4 of both sides, and then I do that over here on the right. Log base 4 of 15. So what that does for me is log base 4 of 4 basically that whole thing cancels right there. It's kind of like that thing's gone. And then you have on the left side x equals log base 4 of 15. But I'm going to figure out with a calculator what that equals, and that is log 15. I'm going to use change of base formula here over log 4. And so x is approximately, where's my calculator? Let me grab that. All right, there we go. Be careful that you close the logarithm there. Log 15 divided by log 4, approximately 1.953, and we'll go 3 decimals. 1.953. All right, now that's one way of solving these. I do want to show you one more way because this is Mr. Bruss' favorite way. So I'm going to rewrite this real quick here. This is another option. I personally don't like my students to do it this way, but I know Mr. Bruss loves this because he loves natural log, and that is, it's not too difficult. You could take either the natural log or just a regular common log of both sides. So we could go natural log of 4 to the x equals natural log of 15. Now here's what that does for you. The power property means the x can now come to the front. X natural log of 4 equals natural log 15, and then you divide both sides by natural log of 4 and you get natural log 15 over natural log of 4, and that gives you the same answer here. See, because it's just using the change of base formula. This and this are exactly the same thing, and you'd get the same answer here. So you could take actually a log base 10 or a natural log of both sides, and it will end up working out the same way. Although I like my students to practice using base 4. If the base is a 4 here, you just take log base 4, and then it all cancels out. The rest of my examples I'm going to do this way, but technically this also works out if you've got Mr. Brust and you want to say, hey, I want to show you how I can do it like you do it because you like it this way. All right, number 5. Here we have what you want to concentrate on is, okay, this is just number 5. Don't get confused with that little decimal there. It's just number 5. Okay, so we have 9 times this. I'm going to put a little box, and I want you to do this. In your notes, you better have this little box around base 10 raised to the 6x. And I'm putting that box around here to show that we're trying to isolate that. Until the until we have this base 10 all by itself, we can't solve for it, the exponent. So now we get 10 raised to the 6x equals 45 divided by 9 is 5. And now we can take the log of both sides. Log what? Log base 10. Well, log base 10 is just log. You don't have to write the base 10 on there because that's a common logarithm. And if I do it to the left, you must do it to the right. Okay, don't skip this step. A lot of kids will skip this step here. So we do that to both sides, left and right side. This is now gone. And you just have 6x equals log 5. And now you can type in a calculator log 5 divided by 6, and you'll get your answer. Just be careful that you did close the parenthesis there when you're dividing by 6, and you get 0.116. So 0.116 is what x is approximately. Number 6. Now you're going to do this one on your own, but I will help you to identify. First of all, this is just problem number 6. Don't get confused with that little decimal there. And then I'm going to put this box around the base. Okay, so remember that. Find the base of the exponent, and that's what you're trying to isolate. So get rid of this 7, get rid of this 5, solve that, and then I'll have the answer appear here in just a second. And there's our answer, negative 0.772. So as you look at these steps here, if you need to pause it, go ahead and pause it so you can follow along with what I was doing. One thing I will say is on this last step, all I did is after I figured out in a calculator what my answer of these logarithms were, then I just subtracted 8 and divided by 9. I just ran out of room here, didn't want to worry about showing those steps. All right, good deal. Now, before I go on, I want to show you a quick little clip of this poor soul playing the newlywed game. Funny dude. Just have a little break here before we finish off our notes.
How many decades will your husband say his mother has lived? Gloria.
10 decades.
10 decades. Gentlemen, how many decades has your mother lived? Daryl, you have a troubled look on your face. What's the matter?
Oh, I don't know what a decade is. 44th birthday, so she'd be
Good.
at 4 years a decade. She'd be 10 decades.
10 decades.
Okay, I love that. hilarious to me. Well, I don't know what a decade is. Okay, now we're going on to exponentiating both sides. I love this term. It's so great to me the way you say this word. It just rolls off the tongue. Exponentiate. Exponentiate. That means we're going to pull these things and throw them up into the exponent. Now, before we do this, and you'll see how this works here, I'm going to box, and I want you to do this in your notes. I want you to put a little box here around the logarithm. So now we're solving for this logarithm. I put a box so our eyes can focus on getting this isolated. So that means our first step is adding 7 to both sides. So we'll have log base 2 of b equals, I added 7, now I have 4. Now we'll do what's called exponentiating, meaning we're going to throw the left side and the right side up into an exponent. We're making these things small. The base, so let me say equals, the base of both sides is going to be a base 2. How did I know how to choose a base 2? It's because of that base right there. That's why. If the base of the logarithm is a 2, then that's the base of my exponent, and I will get log base 2 of b. And over here, I'm going to get 2 raised to the 4. Those are now my exponents. So again, back up here, look here. Left side, right side are exponents. And now this whole thing on the left side, this all cancels because the base of the exponent and the base of the logarithm are identical. So on the left, we have b. And on the right, we have 2 raised to the 4th power, which is 16. There we go. Done. That's exponentiating. Number 8. Now we'll do the same thing. I'm going to put a box, though, around my logarithm. So start off where the L is, and just anything that's in front of that, we're going to get rid of it, and anything that's behind the logarithm, we're going to get rid of that. So this is what we're isolating. Natural log of x minus 6. So let's add 5 to both sides. We'll get a natural log of x minus 6 equals 9. And now we're going to raise it. Now think about this. What's the base of a natural log? It's e. And so we're going to go e raised. Now, don't write this down yet. Watch. E raised to the natural log of x minus 6 equals e raised to the 9. Okay, now I could do this. I'm going to show you kind of a little shortcut here. And when you have to show your work, you could just do this. Watch. I'm just going to go like this. E raised to blue, 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 and then e raised to the 9th. So I did that. I'm kind of cheating my way around showing some work. I'm just going to make both sides become the exponent. And now that means that the e and the natural log cancel each other. That's all gone. And on the left, I just have x minus 6. And on the right, I have e raised to the 9th power. And so my final answer would be e to the 9th plus 6. Or I could get the approximate answer. Let me grab my calculator and figure that out. And that is, big number, 8,109.083. 8,109.083. That's what I had, right? 8,103. Yeah, good. All right, there we go. Answer done. Okay, now you're going to go for number 9 here, all by your lonesome. Go ahead and pause this video. Wait, don't pause yet. Let me help you out here. Isolate, remember your box? We're trying to isolate this puppy right here. That's the logarithm you get by itself. Okay, go ahead and pause. Okay, here you go, and the answer is n equals 13. I tried to show my steps here for you, and I even showed the point here where I'm exponentiating both sides. I put in red, this red 3, so you can see that a little better. So if you're not sure about this one, pause the video so you can get all those notes down if you did not get 13. All right, the last part of our notes is this cool thing called Newton's Law of Cooling. Some of you might have used this in some science classes here and there. It's a really cool application process of some exponential functions, and we're going to have to use some logarithms to solve these. I tried to make this as easy as possible for you in your notes, so you just got to fill in some blanks here, and that is that this left side over here, this represents the temperature of some object after time t. So get that filled in. T of S, when we have this little s, the S is standing for the surrounding environment. There's what the temperature is of basically of the room that the object is in, or outside if the object's outside. Then T naught, this little sub-zero right here, that is the initial temperature of the object when no seconds have gone by, or no minutes, or no hours, whatever we're dealing with. And then K is a constant that changes depending on what type of material it is. So if it's if it's like the object is a rock, it's going to cool down at a different rate than a cotton ball, or it just kind of depends on the material properties of the object. And then t, we've talked about that already. T is the amount of time. Typically, we're going to do, for our problems, we're going to do minutes, but it could be in seconds or hours, just depending on what you're dealing with. Usually, we'll say minutes that have passed since the object began cooling. All right, so get the rest of those words down if you don't have them yet. We're going to do a practice problem with this, and then I'll let you get started on your practice and your application. So good old Mr. Brust here. Mr. Brust loves pizza. Let me get this guy out of the way. Mr. Brust loves pizza. And when he eats the pizza, let's pull him out of the way. When he eats the pizza, the problem is he doesn't understand Newton's law of cooling, and so he burns his tongue because he eats it too fast. He's impatient. So what we're going to do is help him out. We're going to figure out how long he's got to wait in order to eat the pizza if it's safe. Now, 120 degrees Fahrenheit, we're going to say that that's safe. It's cooked at 425 degrees. The room temperature is 72. Okay, so you've got all this important information to work with. Let me go to this next page here because I have the formula. And so here we have our formula, and we're going to write out some things. Let me highlight some important stuff here. That there, we've got 425 degrees. What else we got? We're trying to figure out when is it going to 120. We've also got, let me change colors here. We've also got that after 2 minutes, that the temperature is 285 degrees. Okay, so what does all this information mean? It means we can start writing out some stuff. The room temperature is 72. Well, which one is that? Is these? That's T of S. So our T sub S is going to equal 72. What about the 425? That is how hot the pizza is right when we're taking it out of the oven. So that's our T naught, our initial amount. So our initial temperature is 425. Okay, what else do we have here? The 120 degrees is what we want the pizza to be. So let's say this. We're going to say that the T of little t, we're trying to get it to equal 120 degrees eventually. What else do we have? We wait 2 minutes. So we're going to say that little t is going to be 2 minutes. And that happens if, let's see, our temperature is going to be 285 degrees when we have a little time temperature of 2. Okay, so here's all of some information we can use. What we need then is we need to figure out what this constant is before we can solve for anything else. Oh boy. Okay, so here we go. Let's take this information and plug in everything we know. So let's plug in the information that we have, which is 285. And then this is going to be a 72 plus, because the surrounding temperature is 72. How much was the pizza? How hot was it at the beginning? The initial is 425. We're going to subtract the surrounding temperature, which is a 72. And now we have times this by e raised to the k. We do not know what the material object is, times 2, because we're multiplying by 2 minutes. So after 2 minutes, t here, we have a temperature of 285. This will now let us solve for negative k. So subtract 72, and that is 213. And I've already actually done these numbers in a calculator already because I wanted to speed this up. 425 minus 72 is 353. And then we have e raised to the, let's just change this to negative 2k, since that's just multiplication there. And now we divide both sides by 353. And again, I did this in the calculator, so this is speeding this up. And I get 0.603. Let's go a couple more decimals. I'm going more decimals just because I'm going to end up taking a logarithm of both sides. And so I don't want to just go 1 or 2 because I don't want to round too early with my answers. And then I'll have e raised to the negative 2k. Okay, and now my next step is I will get rid of this e here by taking the natural log of both sides. When I take the natural log of the left side, I get a negative 0.505. Let's go 17. That's a lot of decimals. And then if I take the natural log of the right side, I get negative 2k. Last step is to divide both sides by negative 2, and that will give me that k is approximately 0.252. Let's go one more decimal, 6. 0.2526. All right, that's an important part here. Okay, so we've got what our k is. I'm going to, let's see, I'm going to copy and paste this over to my next slide because we need to use all of this information here. Okay, now I've got all of this, and I'm going to move my k over here. I got my k is 0.252. I rewrote this problem because if you look back here at the instructions, we're looking for how long. You notice this here? We're looking for how long, after taking the pizza out, does Mr. Breast need to wait for it to be 120 degrees. So that is my t value. Let's come back over to this. So I'm now solving for t when I'm looking right there. I'm trying to solve for that t value of this new equation. So I reset everything in, except now I have my k. Now I'm not going to solve the rest of this, solving for t, because you'll basically do just what we just did before when we solved for k. You'll subtract the 72, divide both sides by 353, natural log both sides, and blah, blah. You'll solve for your time of how long Mr. Bruss has got to wait. And we are done with Unit 9. Can you believe this? It's over. That was so fast. Now, our next unit, Unit 10, will be by Mr. Brust. And just in honor of students who have to learn from Mr. Brust, I just feel so bad for them. It must be incredibly confusing for you poor kids. And so I tried to find a video clip of someone who's confused in math because of whatever reason, probably their teacher. So this is in honor of that, and this is Mr. Bean signing off. Rock that master check, and I will see you back in Unit 11.
Okay, here's your homework. First let me tell you the directions. What's 4 take away 5? 1, 2, 3, 4, 5, 6. Take away. What's 6 take away 1? 1. No, you take away, so you take away 1 out of 6. How much does it equal? What's 10 minus 1? I don't know. 1, 2, 3, 4, 5, 6. 6, 7, 8, 9, 10. Nope. Take away 1. How much is it? 1, 2, 3, 4, 5, 6, 7. Nope. 1, 2, 3, 4, 5, 6, 7, 8. And 8 and 1 more. And add 1 more. How many does it equal? 1, 2, 3, 4, 5, 6, 7, 8. 1. It makes 9. See how you take away? You take away 1 and it equals 1. Do you get it now? Yes.